Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So today we will be looking at best first search, and we will be looking at the applications of best first search to finding the shortest path. So let's start with the usual definition of a graph. A graph is a set of vertices which is a v1 to vn, and we have been given the edges which are a set of pairs of vertices. In the basic definitions, we have a graph that is given as v comma e. V is a set of vertices and E is a set of edges. If uv is in the edge set, that implies that vu is in the edge set. In this case, we call this one as an undirected graph. Sometimes for the edges, we can have some weighted allocated to it, and we call that as weighted graph. If there is an edge from u to v, then we say v is a neighbor of u, and the number of neighbors a vertex has is called the degree of that vertex. For example, here we have a set of vertices represented as nodes in a plane. Usually graphs are represented in a pictorial manner in this form, where the vertices are represented as nodes and the edges, which are pairs of vertices, are represented by edges, by lines, straight lines or curved lines at joining those two vertices. For example, here say is an undirected graph where there is an edge between A and B, meaning that A comma B is an edge. Similarly, there is an edge between B and E, that means there is a B comma E is an edge, but there is no edge between B and F, what implies that B comma E is not an edge in this graph. We can have weights here, and we can also have this directed weighted directed edges. Directed edges implies that there is an arrow which says that there is an arrow from D to A, implies that D comma A is an edge, but since there is no directed edge from A to D, or there is no arrow from A to D, that means A comma D is not an edge. As we have seen in the last 3 lectures, graphs are a very important combinatorial objects. They are very simple, but yet very general. Many real life problems can be formulated as graph theory problems, and so understanding the general structure of graphs is a very important aspect in the field of algorithms. Now, one of the most basic notions in graphs is the connectivity. We say that two vertices are connected if there is a path from one vertex to the another. In an undirected graph setting, if there is a path from u to v, then there is a path from v to u. So, if u is connected to v in an undirected graph, then v is also connected to u. So, set of all vertices that are connected to u is called the connected component of this vertex. The connected component, the graph can be seen as a disjoint union of these various connected components. Another very important concept is the concept of tree. A graph, connected graph that does not have a cycle is called a tree. A tree has some other properties. For example, a tree always has the number of vertices minus 1 edges. It also has that if a tree touches all the vertices, then it is called a spanning tree, and every connected graph has a spanning tree. In the case of directed graphs, things are slightly more complicated. For example, if there is a directed path from u to v, it does not mean that there is a directed path from v to u. So, if we say that a graph has no cycle, means a no directed cycle, in that case we call that graph acyclic, and we have similarly a notion of strongly connectedness depending on the directed paths. The problems of this directed graphs, undirected graph setting are that given a graph, is this graph connected, or given a graph, does it has a cycle. In this case of undirected graph, it does not matter what kind of cycle it is, just a cycle. And also given a graph, can you find the spanning tree? In the last 2 lectures, we saw that the answer to all of them can be done within a algorithm called depth first search. But as we have seen that depth first search is just an algorithm for finding one spanning tree. The similar set of questions can be done for undirected graphs, and again we will get something for this depth first search. Depth first search is very useful for understanding whether a graph is acyclic or not. Another important notion which is very important is the concept of distance. So, I have a path from say u to v. We say that the length of the path is the number of edges in this path. So, distance between u to v is the length of the shortest path from u to v. For example, here say we have this graph and consider this path. This is a directed path from G to A. The path length of this path is 4, whereas this is not the smallest one because I have a smaller path. The question is that what is the shortest distance between u to v? So, I have given you a vertex u and a vertex v, and I ask what is the shortest distance from u to v. Also, what is the shortest distance from any vertex from v? So, it is something like in the case of real lines, if you have noticed carefully, beside the tracks they have the post which writes down what is the which is distance from that point to the nearest big station. So, you say you are close to Delhi, it will say that what is the distance from that line to Delhi. But it turns out that there can be many paths from that station to Delhi. So, what is written there? What is written there is the shortest distance from Delhi. So, for in this case say v is Delhi, and we want to find out the distance or the shortest distance of all the other stations from Delhi. And how will you do it? We need to have another algorithm, what is known as the best breadth first search. Breadth first search is exactly depth first search, and it is used to produce a spanning tree. It has a lot of applications. Depth first search had this notion that it started from a vertex and looked at it, ran as long as it could till it hit a blocking point or a dead end, and then it came back and looked for it. So, it searched in a depth first way, it went for the depth. The breadth first search does the opposite. It first looks at all of its neighbors and then all of their neighbors and so on. So, the idea of breadth first search is again start from a vertex, find all its neighbors. Let us look at all the neighbors of its first vertex and so on and so forth. So, the breadth first search is very similar to the depth first search, and finally, it will output a spanning tree. So, just in the case of the depth first search, we had used the concept of a stack. In the case of breadth first search, we will have to use something called a queue. A queue is a data structure which basically kind of represents how a queue occurs. So, how does a queue occur? Say you are gone to a shop and you are standing in a queue, or a ticket counter and standing in a queue. The idea is the person who enters first is the first person to leave. So, thus it is called this first in first out kind of concept. In the case of stack, you remember it was like a pile of books. The one that came last, it was put on top, and when we had to take it out, we had to take that one out first. It is called the last in first out, whereas this one is a first in first out kind of concept, where we have a queue which represents how these things will enter and exit. So, in other words, whenever I have to put something in the queue, I will put it at the end of that queue, and whenever we have to take it out, we will take out from the front of the queue. Just for our explanation in this lecture, I will not be taking it out, instead I will moving a pointer which will kind of indicate where is the start of the. Okay, so, let us look at an example of this breadth first search. Say we start from the vertex H. First of all, we color this vertex H and put it on the queue. As I told you that this arrow will indicate what is the start of the queue. Now, we take this first element of this queue, which is H, and we look at all its neighbors. So, for example, it has only one neighbor G, and it takes that all the neighbors which is G and puts it in the queue, and once it is done with H, it just moves it out. So, to indicate that, we have moved the pointer to G. So, now G is in some sense you can think of the first element of the queue. Now, at this point, what would have depth first search done? Note that till this point, depth first search and breadth first search would have been done the same amount. At this point, depth first search would have found out one neighbor of G, looked at it, then we have looked at another neighbor of that element and looked at it and went on. But instead, in the case of breadth first search, what is done is that we will first look at G and look at all its neighbors. So, what are these neighbors? Its neighbors are E and F. So, it first takes the neighbor E and puts it in this queue, and it takes its neighbor F and puts it in the queue, and when it is done, so now G has put all of them in the queue and it is done with it and throws away G out of the queue. So, at this point we are left with a queue when we have E and F. So, think of it this way: G has looked at all its neighbors, it has placed all its neighbors in this queue. Now, it is going to take out the first element of the queue, which is in some sense the first element, the first neighbor of G, and it will look at all the neighbors of E. So, instead of looking at one neighbor of E and then going and then to that neighbor and then going one more from that neighbor, instead of that, what it is doing is that it is starting at a vertex and taking all the neighbors of that vertex. So, when we are at that neighbor E, it first look at say the neighbor C, we puts it in the queue. If since C has not been looked at all, then again it looks at another neighbor B, it has not looked at it at all. So, since B is not blue, and again it also looks at this vertex D and it will put this vertex D in this queue. At this point, E has been E's work is done, and then E would be moved out of this queue. Now, what is the next one? The next element in this queue is F. At this point, F has two neighbors. So, it looks at first this neighbor, but since E has been already been marked blue, it will not take this neighbor, and again same it will be doing for the neighbor which is D, and in that case it would be done with it and will move to C. Now, C again will have these two neighbors, that will C which has done, and then will move to D, and D will have its one neighbor which it finds and so this way we will be getting BFS tree. Let us take a small break now. After the break, we will look at the applications of breadth first search. Welcome back after the break. Before the break, we saw the algorithm for breadth first search. The basic idea is that as soon as it looks at a vertex, it looks at all its neighboring vertices and then goes accordingly. So, that is why it is called the breadth, because it looks at the breadth first instead of the depth. So, just to look at the pseudocode of it, the operations of the queue are that we have two operations. We have this NQ, which basically puts the element in the back of the queue, and we have another thing called a DQ, which will remove the earliest from that queue, and using that we can obtain a pseudocode. It is exactly same object. We first start with a queue which is empty. We will first color vertices gray. As soon as we see we put the first vertex in the queue, then as long as this queue is not empty, we first dequeue that element. Once we dequeue that element, we will look at all its neighbors, and now here is the important part, that for all neighbors it will do that. For all neighbors, if the color is gray, it would basically that vertex has not been looked at, it would color this vertex blue, it will select that edge, it would enqueue that edge into the stack, and the usual thing of removing it from the neighboring set. So, instead of looking at just picking one vertex and doing something, it looks at all the vertices and puts it together. So, what is the advantage of this algorithm? Intuitively, the advantage is that, say you are at your home and you want to check your neighborhood. There is two ways of doing it, correct? You take a long walk, you walk till you find something, and you find out what, and then come back a little bit, and then again go till you hit another dead end, and so on. That is one way of doing it. The other way of doing it is, you first look at all the things that are to be done at a distance of less than one step from your place. Then once you have done that, or just one block away, you look at all the things to be done. Then you go to the pick up one of the blocks, you go to that block, and you look at all of the places that are close to that block, and so on. So, you are just not taking a long walk, but you are searching it in a very more systematic way in some sense. So, this is what BFS does. Of course, just like the case of DFS or depth first search, BFS also checks for the connectivity. If U is connected to V, then BFS will someday or other find out the edge or directed path from U to V or V to U, whichever you are looking for. It is exactly same as what DFS does. There are two kind of edges only. There are tree edges and non-tree edges, and nothing more complicated than that. There is nothing concept of back edges or forward edges. Although these non-tree edges can be looked at as some two classifications of edges, which we will see later on in possibly next lectures. Regarding the runtime of this algorithm, again since each edge is visited at most twice, so the runtime will be again linear in the size of the input, which is order V plus E. So, let us look at an application of BFS. So, for all vertices in the graph, I want to find the shortest path from V. This is something, as I told, is a very important thing. One can imagine why. The idea is that you run the BFS algorithm and note the distance by saying the distance of any vertex is one more than the distance of its parents. Now, what do I mean by the distance? Just to indicate it. So, here say I have this graph, and so on. Now, if this is my vertex V, so I am looking at all the graph, all other vertices at distance from V. If this vertex is at distance I, then what is this vertex is? The claim is that this vertex must be at distance, this is I and is I plus 1. So, this vertex must be one more than the parent, which is this, and that is basically how we would try to find out. Let us, for example, do the same thing, go over the BFS algorithm, but this time we maintain one more counter. So, we start with H and we say that the distance of H is 0, because of course, distance of H from H is 0, and we are trying to find out the distance of all other vertices from H. Now, we look at the first vertex here, which is H, and look at all its neighbors. It has only one neighbor G. So, we take that G and put it in the stack, in the queue, and since G is being approached from H, so we say that the distance of G from H is whatever distance of H was from itself plus 1. So, which is in this case 1. Now, let us look at the vertices of G. Now, this G I will be looking at the two neighbors E and F. So, we first look at E. Now, E is untouched, so we put it back, and at the same time, since E is being approached from G, so distance of E from H is distance of G from H plus 1. Distance of G from H is already noted as 1. So, distance of E from H is 1 plus 1 is 2. Now, G looks at its other neighbors, which is F, and same thing, F being approached from G. So, I will note the distance of F from H as 2. Now, let us look at the vertex E. For vertex E, it has 3 neighbors C, D, C, B and D. So, look at C, and now distance of C is from, I write it as 3 because it is distance of E plus 1, which is 3. Now, one might ask that why is the distance of C from H 3? Why can't it be lower? How can it be lower? It can be lower if, say for example, there was a path from, there is a H from G to C. If there was an H from G to C, I would have got a distance of length just 2. But if there was a path from G to C, then C would have been discovered when we were working with G. Then C would have been a neighbor of G, and hence C would have been listed right there. So, that is basically crucial, that if something is at distance k, then this vertex will surely have to be found out by a vertex of whose distance is k minus 1. So, let us go over it again. So, here we are looking at this edge E, vertex E. We are looking at vertex E, we look at the second neighbor of E, which is B, and we write it as distance from B to H is again 3, because distance of E is 2, and so B is 2 plus 1 is 3. Similarly, for D, and now we look at F. F of course does not have any edge left to a untouched edge, and so we do not change anything. Similarly, for C, and similarly when you look at B, we will have an A. Now, B is marked as 3, so A must be marked, distance must be 4. Again, to repeat my argument, why can't A's distance be 4, be less than 4, which is a 3. Now, A's distance can be less than 3 if that means that there is a path from H to A of length 3, but if there is a path from H to A of length 3, then that means there must be an intermediate vertex at distance 2 from which A can be approached, and in that case when that vertex was being looked at, A would have been discovered, and that was not the case. So, in other words, this is how one can use the BFS to find the shortest path from edge to any vertex. The runtime of this algorithm is also very simple. It is again just order v plus e, because it is the BFS only. So, this BFS now therefore can be used for finding the connected components in an undirected graph, just as DFS does. It can be used to check if there is a path from u to v, again DFS would have done the same thing, and it is used to compute the shortest distance from any vertex. This is something that DFS would not have been able to do, but breadth first search can do it. To summarize, we did looked at the breadth first search algorithm, and then we looked at the application of breadth first search to finding the shortest path in a graph. So, this brings us to the end of this lecture. In the next lecture, we will be looking at more graph algorithms. Thank you.